At the back, can you hear me better like that or better like that? Is there a difference? Is there a difference? Maybe there is. Pressing the button, that always makes a difference. It goes beep, it must be good. Okay, so I'll leave it like that. Is that okay at the back? Great. Okay, fasten your seatbelts, we have a lot to get through. Perl memory. Who's encountered this? Okay, and this? This? Generally, it's just this. It's taking too long. Who was in Paul's talk earlier? Yes, great. Paul's good. So I want to have a quick recap on process memory to clarify something. You've got a pencil and paper. We're going to be studying these for a while. This is a representation of process statistics. Not very useful. This one's a little easier. But does anyone know what units those numbers are in? So PS is getting better, but again, what units? So top's good. Yeah? You can use top and it gives us a nice sensible number. But if you really want the details, then you can use on Linux this proc status, and the VM size is the one you're interested in. Now, VM RSS is how much is currently and in physical memory, but that's a different topic, and people get confused about that. Where all your Perl stuff is in that bit there. So, who's heard of a segmentation violation? Yep. These are the segments. This is what it refers to. You have your main C code, read-only data, read-write data, heap, and the heap grows as you use more and more Perl stuff. You have a bunch of shared libraries mapped in, each has read-only, read-write, and code and stuff. And then you have C stack at the other end. Now this is not to scale, because if this is a 64-bit machine, there's terabytes in those gaps. So if you want to look a bit deeper in what's in each of those segments, this plot maps shows you one line for each of those segments. And you can see the permissions there at the top, read, execute, read, write. That's for your code and your data. And you see your shared libraries all mapped in. You go one step deeper and ask for more information about each one of those segments. The key point here is that there's the size of the segment, and then there's how much is physically in memory at the moment. And I keep belaboring this point because people get confused about the two. If you're concerned about how much memory your process is using because of your Perl data structures, you're not interested in the resident set size. The only time you want to know about the resident set size is if you have a bunch of processes that are forking off and you want to know what proportion of the stuff is being shared, or if you have one process on the system that's using more memory and forcing others to get pushed down. That's not what we're looking at here. So from the process's point of view, memory is just one contiguous block, and it can access it however it likes. Under the covers, the operating system is working like crazy, performing some magic, producing physical pages of memory for you when you need them. But when the program's doing something else, it'll take them away and give that physical page to another process. So here's an attempt to kind of show that. So the green pages are pages that are actually in memory, and the yellow ones are pages that the operating system has given to something else, or they just haven't been used yet. So don't use resident set size. I think I've made that point. The reason it's important is there are some modules on CPAN that purport to tell you how big the process is and to monitor the process, but they're actually measuring the resident set size. So the thing about the resident set size is that your process can be growing, but the amount of it that's resident can be going down. So you get totally confused. So what you really care about is the heap size, or is the total size, and in terms of Perl data structures, you care about the heap. So, malloc and the heap. Make a good jazz band. So this is your Perl stuff. All your Perl stuff is in there. Now, for Perl, in order to access that heap, Perl uses malloc. So your Perl code needs some memory, and Perl asks malloc for some memory. So malloc then asks the operating system for a new chunk of heap, a bunch And then malloc manages those. It chops them up and dishes them out to the Perl program in little lumps. But it never gives it back to the operating system. Well, not quite, I'll explain some cases. But basically, there's a lot of chit-chat between Perl interpreter and malloc. Give me some memory, free some memory, give me some memory, free some memory. But it very rarely gets returned to the operating system. So, let's change tack slightly now and look at what these internal data structures inside the Perl interpreter are. So they're divided up into three kind of types. We talk about heads, bodies, and data. So the heads, you have an integer in that top example. Now an integer in modern Perls doesn't even have a body. The body is kind of superimposed on top, so it's one little structure. A string has the header, the body, and the data. So the body kind of describes the information that Perl needs to talk about the string. And then if you have a number with the string, then that middle body bit kind of grows. There's extra information tacked on there. Now it gets a bit more complicated with arrays. And you have the data for an array is the set of pointers that point to the SVs that are in the array. And then a hash just starts getting a bit crazy. There's just pointers and structures all over the place. Globs, symbol tables, subs. I'm not expecting you to learn this. What I want you to see is that there's lots of tiny fragments of code with a whole bunch of pointers pointing between them. Now, if you want to look into what one of these structures looks like, Devel peak. Devel peak has been kind of one of the best tools for looking at an individual scale. So here's a hash, and we can look into the hash. There's not much flexibility in what Devel peak can give you back, but it gives you a way of looking in. Now, another little thing to note here is whenever you have a string, you almost certainly actually have a little more space than the string is currently using, because Perl and malloc just optimize the way, if you ask for a bit of memory, it'll round it up to the nearest useful chunk. So if you have all the strings, of course, then there's lots of these little fragments lying around all over the place that are kind of wasted, but it's the most efficient way of doing it. If you want to know how much memory is being used by the data structure, then one of the best tools that we have is Devel size. And Devel size chases all these pointers. It has the logic in it to chase all these pointers, and it chases them around, so you can give it a particular Perl variable. In this case, I'm just giving it a constant 0. So right, 24 bytes. Or an empty array, 64. Empty hash, 120. And then an array with a bunch of values. And it just gives you this number back. So it has in it all the smarts to chase all the pointers, and it gives you back a number. Now that's grand. But it used to be kind of crazy about what pointers it would stop following. It didn't have sensible rules for how much data it should follow. So it would easily end up following too much or not following things that you wanted it to. Now, because malloc has a bunch of overheads and is fairly slow, for things, Perl internals that are of fixed size, Perl now uses arenas. Arenas are pre-allocated chunks that are chopped up into whatever it is that you want to dish out, and you can dish out fast because they're pre-allocated. So Perl has arenas for all the different sizes. Two key points about this is it's another source of space that's getting consumed that you can't see. And another point is that if you have a program that, these arenas never get freed. And they don't use up a lot of space, but they never get freed. So if you have a program that creates 1 million arrays, and then you free them all, you will have arenas for those 1 million array bodies. And you never get them back. They're just sitting there, ready for you to create another 1 million arrays. But you don't want to. So this is another source of data that's hidden. That's just a summary. I've said all that. Any questions at this point? Just going silence. Memory profiling. So I did this profile at MIT Conf, you might have heard that. And people kept saying, what about memory? You know, this is great for CPU usage, but what about memory? Why can't you profile memory? So I scratched my head, and a bunch of other people scratched their heads. And well, what does it mean to profile memory? You know, perhaps we can track memory usage going up and down as the program executes. And so Nick Clark did some experiments with this, intercepting the malloc code. And it turned out not to be very useful. It kind of, memory goes up in obvious places, and it goes down in obvious places. What you really need to know is what's holding the memory at any given time. So, the only sensible thing to do, oh yeah, before I get into that, also, Perl hides memory in strange places. It wants to over-allocate in order to save time later. So this will lead to some interesting surprises. So there's a constant string that we blow up to 10 meg. You call the function and there's 20 meg being returned. Does anyone know why? So there's 20 meg being used after the function returns. Well, 10 meg is used because Perl compiler helpfully did a compile time optimization and built that 10 meg string at compile time. There's another 10 meg being used because the lexical variable, the buffer space, is held. It's not free. So the buffer is there in order that when you call something again, it doesn't have to allocate memory again. It's there for you, so it runs faster.
It's already using 30 megabytes at compile time.
Yes, I know. I was kind of glossing over that the initial point. So yes, it is already using a picture at compile time. Of course, compile time in Perl is low. So this comes as a surprise to a lot of people. And then it gets worse. What happens if you recurse? Well, here we do the same thing, but then we recurse 50 times. And there's now a gigabyte still being used. Why is that? It's because the lexicals exist in every layer of recursion. So there's a vast amount of memory sitting there that you just can't see. Okay. So it seemed the only way to actually get into this, to have visibility of this stuff, was to dig into the Perl internals and actually dump the whole lot, chase all the pointers. So some kind of crawl and dump approach was needed. So I had this plan, crazy idea, to take Devel size, which had the logic to chase the pointers, and add a way of kind of hitching a lift. So add a callback mechanism, so as the Devel size chased around, it could call back to a function that would build up or stream out information about where it was. String that to disk and then write some tools to analyze it and visualize it. Now, that's worked, and there's something there, but the whole thing was built as a set of hacks. It was hacks on top of hacks. And it's getting to the point now where the hacks are just too painful, and they're slowing me down. I don't want to do this because it's just too much of a mess. So I kind of need to reset a bit and rethink the direction. So, what does it do? I'll give you a demo in just a second. But it will write out a stream of information, and that stream of information can be visualized in various ways. Rather than talking about all that, I'll just do a demo. To talk about that, let's just do a demo. Who wants a demo? Yay! Let's have it. Right. So, in order to Devel size looks exactly like Devel size, unless you set an environment variable called SizeMe. That's just so here. Right. Okay. So here it's right out. It said there's an SV and it has an address and using 24 bytes. Here's a string. So the string is a PB. PB, it has an address. There's the head is using 24, the body is using 40, and the length is using 56. Now that's not a 56 byte string, you may observe. But that's Perl over allocating on your behalf. Numerical value, so here's some numeric value, there's the address, there's the head and the body. What about a numeric value that we print, so we use it out as a string? Well, here we just have the head and body, but now we have a head, body, and an SVLN. So it's allocated a buffer to hold the cached version of the number. What about the data structure? So here's an array that's got a number of string and a floating point in. So here we have the array. There's the head, the body, there's the array of pointers. And there's two elements in it. Oh, sorry, the maximum index is 2, so there are 3 elements. There's the integer, there's the string, and there's the number. Now, if I change the SizeMe to a pipe, then we'll see the token stream. So the token stream just looks like that. And it's what's happening here is as SizeMe calls the pointers. Whenever it wants to emit a piece of information, it then works backwards up the tree to reach the last point that it emitted a tree node, and then recurses back downwards, emitting the nodes to build the tree, then emits back. It's all a bit sort of recursion inside recursion. But you end up with a stream of tokens like that that's basically describing a tree from the leaves upwards in real time as it's running around the tree. But that's not very useful. What we want to do is store that, so now we'll pipe it into this program, and we'll ask this program to produce a textual version. Now this textual version looks very similar to the previous textual version you saw, but it's done a bit of decorating of the information and some minor tweaks. And you can see here that it knows the total size. As the tree has been built up from the leaves back to the root, when you get to the root, you have the total size of the whole structure. But that's, you know, looking at pages of that gets boring very quickly, so wouldn't it be nice if we could view it as a graph? And here you can see that one of the things that bit of software did as it analysed the stream coming through was do things like work out that this is an array, so these are indexes. So it's showing the index for the array. Now, let's try this one. So here this is a hash. This is an array. There's an array containing two hashes, both with the key foo. So there's an array. This is the reference to a hash with the element, and there's the foo, and there's the foo value, and the other foo value. And here is the shared key. Those two foo keys are being shared. So Perl really uses the memory for each hash key. So you see here, one is a solid line and one is a dotted line. So inside Devel SizeMe, it's keeping track of things it's seen before. So, and that will make more sense for this next one. So here, the data is a hash, and in the hash is a reference to some global variable. So we don't own that structure. And what we get is it's followed the structure, but then it's got to this point and says, well, I'm not going to follow that because I haven't seen all the references. The ref count is 2, and I've only found one pointer to it. So I'm going to say, well, that's off limits. Now, let's look at a subroutine. So here we have a subroutine, a factorial. Just basic factorial, and then we take the size of that. And what we get is a subroutine. So that's what a Perl subroutine looks like. So you can see all the stuff owned by the subroutine, and all the things that are shared. And like, you know, that has 122 websites. So this is cool. Now, let's do the same thing, but this time we'll recurse. Yeah? So if we look back here, we have all the ops, and this is all the sort of package stuff. And up here is the pad list, so these are our lexicals. This is the array of the lexical names, and these are the lexicals themselves. Notice there's only one name variable, we only have one variable ourselves in here. But there's actually a whole bunch of lexicals that Perl has created to hold temporary variables and hold constants. So for example, this one here, that one is an SV of one of these, they're sort of hidden lexicals. Now if we call this subroutine 3 times, we end up with this. And what's happened is that the pad now has, or there are pads for each level of recursion. And you can see here the size, it's 296 for these extra levels of recursion. So every time you recurse, it's 296 extra bytes being used. Now, let's have a look at the package. Now this sometimes, oh, so this is starting to get beyond the pretty, it's more pretty than useful. You wouldn't actually want to need to examine this to get information out. But there's more information in here than we really need, so there's a mechanism in Devel SizeMe to hide sort of the less interesting stuff, like the kind of the guts of hashes and things. So we'll turn that on and do it again. So it's slightly simpler now. But still, you really wouldn't want to be having to work with that stuff. So what we need is another way to do. So yeah, this might take a little while. That one often doesn't open. You're kind of getting to the limits of what graph is going to cope with. So we need a different way of doing it. So here, I've been calling this function total size of a data structure. We can also call another function Perl size. And that says, rather than asking for the size of a particular structure, just size the whole interpreter, everything, including the stacks and the arenas and the whole shebang. So here it's 720k over 8,000 units, and that's an empty Perl interpreter. Now I'm not going to put that into graphics because it's just done. So what we do is we ask the store function to write a database. So it writes a SQL-like database. And here I'm going to load in moo. I'm also going to call heap size. Now, we called Perl size a moment ago, and that's the size of a Perl interpreter. Heap size goes one level up and tries to include information about the size of the whole process and the size of the malloc space. So, we run that, and then what we do, is so this is a tree map of all the memory used by Perl process. Starting with the heap, the heap's using 11 meg. And here is your Perl interpreter. Your Perl interpreter is using 1.74 meg. But over here, malloc is using 9 meg. Well, if you dig in, you see that there's 8.8 meg of free memory that Perl was using while it was compiling, loading the moo and getting things ready, but then it freed it all up. So there's 8 meg of free memory sitting there. This unknown is kind of what I haven't been able to account for yet. That's essentially a bug. So if we go back up to the top and dig into the Perl interpreter, you have the domain, that's def stash, so that's your stash down there. Let's begin. Here are your subroutines. Just blue stuff, constant stuff. And basically, you can kind of drill down. And Paul said something interesting the other day. This is essentially a blame interface. And that's a good way of looking at it. It's built up this tree. Got sizes decorating the tree, and so you're drilling down, following these boxes. So pointing the finger, it's your fault! You can see there's all a bunch of metadata here, but it's all kind of, it's very informal. Now, there's a problem with this. The way the logic works, how much time do I have?
You've got to go half-hour.
Fabulous. So, the way the logic works, as you may remember, it's chasing pointers, and whenever it finds something with a reference count, it says, have I seen this as many times as the reference count? And so if the reference count is 5, have I seen it 5 times? And if I haven't, then it doesn't go in and explore that structure. But if you have a loop, if you have a reference loop, you never get to look inside the structure, because you never account for all the references. So, having called all the main structures, at the end, Devel SizeMe crawls the arenas and checks that it's seen every single scalar. Because Perl has this as a separate space where you can check all the scalars. So it runs through them all saying, are there any that I haven't seen yet? And if it finds one it hasn't seen, then it goes off and digs into that. But the effect is that this tree that you built doesn't have any ref loops in it. All the ref loops, oh, that's that thing I kicked off a while ago. You really don't want to be working on that stuff. So, yeah, your ref loops don't appear where you want them to be. They appear off to one side. So if we go back here, that's one of the things in here. These are your ref loops. So there's 390k in ref loops here. And this is your string table with the shared strings, and there's a bunch of things in it. So if you go inside the ref loops, then there's a part of the Devel SizeMe that scans the arenas, looking to break loops, and it does it. And it keeps on doing it until there are no more loops to break. So this is the first cycle of loop breaking. And in here, there's a whole bunch of things that are ref loops. So this is a part of the Devel SizeMe that doesn't work very trying to blame, you really want the blame to be put in the right place. So that wherever you have a referee, the blame gets put off to one side. Probably fixable. Any questions? Stunning silence. Does this seem useful?
Yes.
Right. But it's not, it's broken. Well, it's kind of useful, but there's a lot of caveats, you know. I mean, I've used it in production for things like, if you're using LPW to grab a file off the website, so you've got a bit of software and it's downloading files. Because of this business of buffers being, the memory used by a buffer is never free, by a lexical variable is never free, it's saved for the next one. So if you download a 5 gigabyte file, well gee, there's going to be lexicals in your code that have 5 gig of space that's not going to be free, just in case you download another 5 gig file. So there's a couple of places in WP that do that, and it was kind of helpful in some production code for us that sort of pinpointed that and changed the code a bit. Okay, so what am I going to do now? Yes. Okay. So the thing about tree map is that it's a very narrow viewpoint. You're at one point in the tree and you're just looking down at what's immediately below. You have a very narrow view of your data structures. So graph viz is very nice for giving you a more contextual view and overview, but it just falls apart at about 1,000 to 5,000 nodes. And it's just not very practical. So I wanted to find ways of visualizing the structure that would be practical. So I found ways of visualizing them. You have to judge for yourself whether they're practical. So one of the things that we'll do is find, so the store program, you can ask it to write a JEXF file, which is a kind of a XML file that describes a graph with nodes and edges. So we write that out, and then we start this Giphy. So, has anyone come across Giphy before? Okay. So this is this is several thousand nodes. It's only 10,000. Now, I did load a Moose program once, and it was like 100,000. But clearly, that's not very useful. So let's see if we can make it more useful. Actually, the colours here, the magenta is ops, and the blues are hashes, and the greens are sleeves. You might have heard of graph layout algorithms. Most of them just can't cope with data this size, but there's one called OpenORD that actually can. So this is running on 7 CPUs. And it's kind of nice to watch. So what it's trying to do is to lay out this graph in a way that allows you to visualize the structure. It's just nice to watch.
It's very like it's like some sort of biology experiment.
Yes, it's in that fashion. What are the colours mean? So magenta is ops. So if I do this, then you see that's that's an op. If I do that, I can't get to the control. Ooh, it's just there. Let's move it out to the side because things are clear. So that's an array, and these are a bunch of values, and that's a magic. Yellow is magic. I should have used orange, sorry. So here you can see these blue things are hashes, and then there's a bunch of variables in there. So this is kind of cute, but again, it's this thing about being very pretty but not very useful. So let's there's too much complexity here, as you can tell. But what Gephi allows you to do is things like grab a bunch of these and now if you can imagine an algorithm working away, identifying all the leaves of a given cluster, and grouping them, and then repeating all the leaves of the cluster and grouping them, you could collapse inwards this whole graph. And then when you've done that, you'd be able to lay them out much more neatly, and then drill back down to the areas you're interested in. The sizes, by the way, are the log of the memory usage, so bigger blobs and more memory. Because I tried it without the log and it was just crazy because there's loads of tiny things and stuff. So these things with the yellow, for example, one of these with the yellow is your environment variables, and one of them is the signals. So, anyway, it doesn't matter. So, this is kind of where I'm at. I've just been tinkering with this. This is very much a part-time messing around project for me. But as I said, oh yeah, these brown things. That's malloc. That's your malloc over here. Stuff that's been free. So, there's too much data here. There's too much data to actually extract usefully. So the tree map is kind of a useful tool, and if I can resolve the ref map, the ref loop issue, to put that somewhere more useful, that would be good. But it still feels like there's a lot more to be done with this data. There's a lot more that could be extracted. But I think what's needed is to have a database format. What I'd like is to sort of have a database format that is very informal, and Paul's code could also use a database format. So we could possibly use the same format. So what I'd like to see, or one of the things worth exploring, is to have a database format that captures these, because essentially it's a typical graph. You have nodes, and you have edges, and a bunch of attributes on the nodes and the edges. So if you could do that, then other people can start developing modules, and you have an ecosystem around this data format, and people could start writing their own modules to answer their own questions and share them. So, any questions?
As a sort of compromise between tree map and big message circle, do you consider something like that? The radial,
yeah.
It's a tree map that you can kind of go down into, and it shows you a little bit of the neighbours.
Yeah, I haven't, no.
Just
But you're welcome to. You see, so this is the kind of thing where if the data was available in a format with a module that you can interface to it, people would start exploring their own. And I think different visualizations would suit different use cases.
Yeah.
So I'd like to see an ecosystem develop. So, how much time do I have?
16 minutes.
65 years. So, from my take on Devel SizeMe is that it's very focused on memory usage. It's come from that perspective, whereas Devel Mat is focused on structure. So your primary focus was reference loops.
Yeah.
So Devel SizeMe walks all the internal pointers, which is a slightly insane thing to do. It's the poster child of breaking encapsulation. It just breaks encapsulation everywhere. So the internals of Devel SizeMe are just awful. And also clone, you have duplicated code from the inside of the Perl internals. But it's stream-based, so the whole way it streams things out and the way that the data is processed as it's streamed out is entirely stream-based, so it can cope with data of any size. It does support multiple output formats, which is kind of been but it's very informal. The whole thing was a bunch of hacks and big experiments, and that's got to the point now where it's kind of making it painful.
Is there a way to just have it in a program watch specific variables? Because sometimes or specific methods, that something in this method or this particular variable is exploding.
Yeah.
And that's what we want to watch.
Yeah, so can you repeatedly dump an individual variable?
Or the memory usage for a whole method.
Yeah, now there's some support for that, but I haven't taken it very far. There's an idea of the stream has a token in it for starting and ending. So you can then have multiple streams stream down the same pipe. So there's the start of that, and I think that's a very good use case. And it's one of those things where Devel SizeMe's approach works better than Devel Mat, because Devel Mat always has to dump the whole lot. I think that's a fair statement. Whereas Devel SizeMe has the option of just exploring a bit you're interested in. So it's kind of, from my point of view, I think, well, do I kind of abandon Devel SizeMe and contribute to Devel Mat, or the other way around, or who knows? I think this is an ecosystem that needs a lot of exploration and development. So these are some of the limitations of Devel SizeMe. The big problem, the big kind of architectural problem, is that as it's processing a stream of tokens and it's building the tree backwards, it accumulates the sizes up the tree, which is grand because then you can do the tree map visualization, which requires all the nodes to have the total size on them. But you can't then edit the tree, because if you edit the tree, your sizes are all wrong. You have to recalculate. So the existing code needs to be broken up into a bunch of phases, where some phases manipulate the tree, and then a final phase does the accumulation of tree counts to do the tree map. So again, this kind of calls for there to be an ecosystem of people writing and contributing modules that manipulate the tree. So Devel Mat, as I said, focused on relationships. And because Paul took the very sensible approach of starting with the arenas, there's less breaking of encapsulation and less digging around in the obscure dark corners of the interpreter. But it always dumps all the SVs, and also the current user interface stuff has scalability issues if you've done pretty big programs. So, again, I think that scalability issue calls for use of the database. So, I think there's something we should be talking about having a common database format. So if you redid the user interface with an SQLite backend, for example, that would be a relatively simple step. And then that SQLite would be very common, people would be very comfortable using SQLite and do things. But there are limitations to what you can do when you start modeling trees in SQL. Has anyone modeled trees in a relational database? It's not much fun. So what kind of database? So my suggestion is that we do a bit of SQLite, but also somebody, perhaps me, perhaps you, perhaps somebody else should work on taking the SQLite data and mapping it into a graph database. Because graph databases, funnily enough, are awesome for graphs. So let me give you a little demo. One of the Neo4j. Neo4j, open source, it's Java, but you don't care about that. It's just a black box, has a web interface, you talk less to it, very simple. And also you can do bulk loading, which would be important. But the thing about graph databases is that they are very good at handling graphs and answering questions about graphs and doing transforms on graphs. So, where did that go? So, what a graph database does is it allows you to express queries in terms of topology. Yeah, so here you have a little visual picture. There's a little visual picture here of the topology you're looking for and placeholders that you want populated with variables. So you can kind of draw little pictures in your query and say, find me all the instances of this topology within the graph. And this is great. And you also do things like find the shortest distance. And guess what? The shortest distance between the node and itself is a refuge. So rather than having to write the code to trawl through a SQL database to try to work out refuges, which would be insanely slow and complex, using a graph database, you get it for free. So there could be powerful user interfaces built on top of this kind of approach. So that's kind of where I'm at. Does anyone have questions about all this?
You promised to talk a little bit about the giving back to the operating system memory.
Oh, yes. Thank you. So, malloc takes from the operating system, but doesn't give back. So, this used to be a bigger problem than it is these days. In order for malloc to give back a chunk of memory, it had to be completely freed, and of course, once malloc has got a chunk and it's chopped it up into smaller bits, it was never really free because there were fragments and things lying around. What happens now in most modern mallocs is that if you ask for a bit of memory greater than some threshold, and I think it's usually 128 kilobytes, if you ask for more than 128 kilobytes, it'll actually won't allocate it from the operating system in the usual way, it won't increase the heap. It'll allocate it as an anonymous memory mapped page, which comes from somewhere else. And when you free that memory, it'll actually free that page. So if you're dealing with single chunks of memory that are very big, like a big string, if the string is over 128K, there's a good chance that that memory will get freed back, because it'll be coming in, the pages you'll be using to hold the string will be anonymous memory map pages. And when you free the string, they'll get freed off. So there is this threshold, and I think I might even have on one of my slides all sorts of old slides. There we go. Memory threshold. So certain applications, this might be an issue that you might be dealing with a lot of 100 kilobyte strings, and you might say, well, let's try this out. The swings and roundabouts, though, because when asking for a memory map page is also more expensive than just asking malloc for an ordinary page. So there comes a point where there's a speed-space trade-off. Is it, in order to be able to get the memory being freed back, are you willing to pay the price of the extra cost of allocating it as an anonymous page? Does that answer your question?
I had a program that grew too big, and my only solution was to fork it. And
Andreas.
yeah.
Hello.
Hello.
I haven't seen you in years. Sorry, carry on.
And it was quite annoying. So I had to rewrite the program to somehow get the data over to a child. Then it was small again, and everybody was happy. I would have preferred to get a solution.
When the child grew up.
No, the child. I don't remember the details, but I would have liked to find out how to get the original program to give back. It wasn't using the memory anymore. It was just a daemon running, and it was 300 megabytes, and it was swapped out. But everybody was unhappy about having this program so big.
So, when you say the memory wasn't being used anymore, was it, had the Perl interpreter given it back to malloc?
Well, I don't know. This is what my question is.
So that's the kind of thing that Devel SizeMe can answer the question. Now, if you run Devel SizeMe as -d colon SizeMe, then it runs in an end block. And of course, if it runs in an end block, then usually all sorts of things have finished. So you end up seeing lots of things that have been freed. Whereas if you run it explicitly and put in a call to say Perl size at a certain point in the code, then you can see what's actually being held at that point. And that will allow you to see how much is being given back to malloc. You can see how much is sitting in arrays. And then hopefully the pre-map will just allow you to put down and blame who's holding it. Questions? We have a little bit more time.
It's available on CPAN?
Yes, it's on CPAN. The version of CPAN is a little out of date. But that's great. It's not very out of date. It was what I used for the YAPC Asia. No, it's what I used for YAPC NA in August. I'm kind of putting it to pieces now, so it's kind of like it's in bits on the garage floor. And I'm trying to summon the energy to put it back together. So I did a straw poll on Twitter saying who wants me to work on Devel SizeMe or DBI from Perl 6. And so far, 7 people said Devel SizeMe and 1 said DBI from Perl 6. So I guess I should do something more. And certainly I'd like to work with Paul and sort of see if we can make some progress together. And then I can offload all my stuff to him.
I thought that's what he was thinking. Sounds like discussion.
Yeah. So you know, it's an interesting thing because there's clearly overlap, and yet there are clearly benefits to the individual approaches. So some exploration is needed. So I think what Paul's code has that my code is lacking is a data model, you know, an actual sort of rigorous definition of what things are. Mine is just a bunch of nodes and links and strings, and this is all just sort of detritus from my experiments. So you know, there'd be value in me adopting, Devel SizeMe adopting your kind of schema, but then putting it into SQLite and then the value you using SQLite and it could all work out very nicely. Two questions at the back.
The earlier graphs you showed with lots and lots and lots of nodes, they all seem to be lots of similar nodes, perhaps using the visual. Do you know enough about the nodes to be able to say these are all similar enough that let's talk about them all? Let's talk about them all together and collapse them and reduce at least some of the confusion and some of the height of it.
Yeah, I think recognizing subroutines, little bits of topology that represent higher level concepts like a subroutine. So, do you remember I showed a graph of a subroutine, and there's a whole bunch of nodes. You know? Now, sure enough, a subroutine is made up of all those bits and pieces, but most of the time you don't care. You just think that's a subroutine. So you want to be able to collapse those nodes into one node and say, well, that's the node for the subroutine. So I think that's the essence of what we need to do, is to collapse these things down. Ideally with the ability to then reopen them up, if you need to, but there's just too much detail at this level. So if we can collapse them down and create higher level concepts, that's where people could write modules that perform those kind of functions. You know, that's what I'd like to see. Sort of an ecosystem of transformations. That sounds good to me. Another question?
Does it handle self-referential data well?
Does it handle self-referential data well? Well, yes and no. So, when you call Devel SizeMe on the data structure, it gives a free, so it follows the reference counts. So it'll only follow data that you own. So the idea is that if you freed the thing that you passed it, then the number you get back is what would be freed as it ripples that free down through the data structure. Probably I'll explain that. So if there's a loop in the data structure, the value that you pass the function gets a sort of a free pass. Its reference count isn't considered. So if you pass it the thing that has a reference back to itself, that's fine. You'll get the whole structure. If you pass it a pointer to a structure that has a substructure within it that has a reference with, you won't see that, because it'll chase down to the node that has a higher reference count, and it'll stop there because it hasn't seen that node often enough. It hasn't accounted for all the references. So if you're dumping the entire process, you do see those because they get spotted at the end when it sweeps through the arenas and double checks all of the scales. But that means that the data structure doesn't turn up in the tree where you expect it to. It turns up somewhere else in this cycle area. So that's something that could be improved. So if you're dumping the whole tree, there should be some rules to say, well, pay a little less attention to ref counts. And that would improve that. But another way of doing it is to dump the data to a database and write some software that then kind of works out, because all the information is there about who's referencing that loop. So you could then stitch things back together. And then if you can visualize the loops correctly, then that's grand. It will appear in the right place. Any more questions?
How does it handle XS code?
Sorry?
XS code, how does it handle?
How does it handle XS code? It doesn't. Now, you see, if you're dumping the whole process, then you'll see it in the sense that there's memory that's shown as being allocated by malloc that isn't accounted for elsewhere. So you see it that way. Also, I can imagine that in the same way that individual classes can provide helpers for serialization, I can imagine that individual classes could provide a helper that would then describe their internals in a way that Devel SizeMe could then chase through points.
Yeah, I've actually been considering exactly such a mechanism because, yeah, again, Devel has the problem that you find a whole bunch of SVs that don't turn up anymore. So we know these SVs exist and have ref counts, but I could not find a pointer anywhere from any other SV. And a lot of those are because they're just stored in some variable in a piece of C code somewhere. And yeah, having some code in just sort of a standard protocol to say implement a method with this name and it will return data in this form, then all the access modules will provide hints to such tools to say here's where symmetric bits are.
Right, thank you very much. One more.
Is it just producing graphs, or has it changed the way you program?
Is it just producing graphs, or has it changed the way I program? But aren't the graphs enough? What colours? They're so pretty. They're so pretty. I mean, who couldn't love that? You know, what I'd really love to be able to do is to do that in 3D and then put on virtual reality glasses. Oculus Rift.
That's the one.
Yeah. So I actually looked at some software for doing that, but you know, it's all doable. And you know, that's exactly the kind of thing that somebody could do if we had this database format. You could do it. And it wouldn't be a big deal because it's basically a bunch of graphs and nodes, and you lay them out with this software, and off you go. But in terms of changing the way I write, not really. But then maybe I was kind of familiar with the issues anyway. I think the fundamental problem with Perl is that there's ref loops, that's the big one. The smaller one is that there are so many tiny little fragments of memory being used all over the place that to actually get a handle on this. And it's like, if you wanted to improve the memory usage, you might have to make some of the tiny changes. So I think what has changed, for example, is that the first time I started working on this and visualizing it, I found a bug in Perl 5, the threaded build. Every single line of code in the threaded build had a copy of the file name associated with it. Now that's been fixed now, but that was a bug in Perl using more memory that was found in Devel SizeMe. So there's those kind of things. So I think that's where some of the benefit will be, is that it can feed back into the Perl developers to show them where there are inefficiencies. And for years, from the early days of Perl 5, there was a pragma called less, use less. But there's a sort of this mythical pragma that people talk about occasionally, but it's never been implemented. And one of the key things that comes up whenever it's mentioned is in the context of, say, use less memory. In order to shift the balance so that Perl is less inclined to optimize for memory, to use memory to save CPU. So maybe this will prompt someone to actually write that. So the idea that whenever you call a subroutine, all the buffers of the Alexa groups, well, maybe if you had a use less memory pragma, those buffers would get freed. That would be a really simple change. It would just require, it would be a simple change to implement, I think, and then it would just require you to say use less memory. So that's the kind of thing that might come out of it. Right, thank you very much.